and yesterday's lecture, we have discussed the very basic definition of welded joints. We have seen types of welded joint, the different types of welding processes basically, which we have seen in the last lecture. And now, so today we'll go for the types of weld. As far as types of welded joints are concerned, we have got two different types, that is lap joint and butt joint. So these are the different types of lap joints: single lap, double lap, parallel. So these are the different types of welded joints wherein lap or fillet welded joints are there. The next slide reflects the butt joints, different types of butt joints, wherein we say that the butt joints are connected end to end. So end to end, in this case, the square butt joint is mostly or widely used type of joint in welded joints, whereas to improve the strengths, in the industrial applications, we generally go for single V and double V, single U and double U type of joints. So these are the examples. Now, as far as design of transverse fillet weld is concerned, I am showing the basic strength consideration, wherein the transverse fillet weld is subjected to tension, a tensile load, because when we say, please concentrate on this diagram, this or this, because this is single transverse, this is double transverse, and now we have taken the consideration as single transverse fillet. So single transverse fillet weld basically is subjected to tensile load. Now when it is being pulled away, in that case, this is the weld area, weldament, what we generally used to call it as weldament. So this is the weldament area, wherein this weldament or weld area is subjected to tensile load. Now we have considered few parameters. Why this is so important? Because based on this particular transverse fillet weld joint or this parallel fillet weld joint, what we'll be getting is the equation from where we can solve any number of problems based on design of welded joint on transverse fillet weld. So this BD, if you are concentrating, is known as a throat thickness. Throat thickness. This is very important because BC and AB are nothing but the size of plate or size of weld, generally used to call it as. Now, solving this triangle will get the area or the throat area which is more vulnerable to the failure. Now, depending upon the basic criteria, stress is equals to load per unit area or force per unit area, we have written this equation as load is equals to throat area into allowable tensile stress, and this is so this is for the single transverse fillet weld. Now the same can be used as for double transverse multiplied by 2. So this is the equation for single transverse and double transverse. Again, the second type of joint wherein we say that strength of parallel fillet weld. So these are the parallel fillets. The welds are applied in parallel filleting mode. Again, the same thing, same area, S into L. L is where L is the length of this weld. So for single parallel, if this is double basically. If it is not there, it is single parallel fillet weld. But these are the basic equations. Now the third type is combination of single transverse and double parallel fillet weld. Now look at this particular diagram, wherein this weld, if applied with the transverse loading, then in that case, these two, that is L2, this fillet of filament L2 will be subjected to shear, and this length L1 will be again subjected to tension. So in this case, since the same load is being shared by both the fillets or both the welds, so we are adding this, because here the type of joint is single transverse double parallel. Single transverse double parallel, that's why we have added these two, and what we'll be getting is the either the size of weld or the thickness of the weld, or sometimes it may ask you about the load. So this is the basic idea of how to calculate the dimensions of a weld for different types of welded joints. The next one I have shown here, circular fillet weld. See the diagram wherein we can apply the torque or the twisting moment. Again, the throat area or the throat thickness will come into existence or come into play, and this is the basic structure wherein the torque, when applied on this particular shaft and the weldment or the weld is there at the joint, then the joint will be subjected to shear stress. Obviously, the shaft will be subjected to shear stress. The next one, since in the previous lecture, I have told you regarding some of the basic questions generally asked for 1 marks. So these are the very basic questions. Weldment in fabricated steel beams are designed for. When it comes to steel beams, fabricated steel beams, then the beams are generally subjected to bending stress at the flange, number 1, shear stress in the transverse plane, number 2. Third, combination of bending and shear. And none of these, because fabricated beams do not get stress. Sorry, this is not the answer at all. A is also true, B is also true, but combination of bending and shear is very true. So the answer is C. The answer is C. Next, next question is, in transverse fillet weld joint, the size of weld is equal to. Now this is the criteria, and based on this criteria we'll be solving another problem. So the answer is √2, that is 1.414. so √2 into third, so fillet weld, this is the answer, C. Next, again I am using the same equation here. A fillet welded joint is subjected to transverse loading. See, both legs of the fillets are obviously 10 mm size, that is S is size of weld, and length of weld is obviously the length of weld along this plate or along this width will be some 30 mm. If allowable shear stress of the weld, the stress is also given. Then in that case, how would you calculate? So this is the basic formula I have written here, and based on this formula, we can get the answer. Okay, PPT नहीं दिख रही है. मैंने शेयर किया मैडम. Okay, just hold it. Screen share. Again I am holding. Application window में PPT को select करके share करिए. Okay, Chrome tab. Now I think it is visible. सर अभी मुझे दिख रही है, मैं आपको मैसेज भेजती हूँ, वो मैसेज आपको दिखेगा सामने आपके विंडो पे. नहीं मैडम, हाँ मेरे पास मोबाइल से कनेक्टेड है. Okay, please. So I think it is now visible to I hope it is working now. Madam, is it visible now? Hello? Hello? Is it visible now, madam? Hello? Hello? Madam? Hello?
Sir, please start now.
मतलब मैडम अभी सब अभी दिख रहा है मेरा पीपीटी पूरा?
Yes, sir. PPT is visible now.
Okay, thank you so much. Shall I start again then?
Yes, yes. No, sir. You start from the whatever endpoint was.
Okay. So I'll start again. Thank you so much. So again, I'm repeating these two questions. A very simple question, that is, weldment in fabricated steel beams are designed for. So the answer is C. In transverse fillet weld, as we have discussed, the answer would be √2 into throat of weld, that is thickness of throat. The next one is a flat welded joint is subjected to transverse loading F. So in this case, we'll be using because see 10 mm size of, that is the size of weld S, and small L is 30 mm. Stress is given, so we can use the simple formula, that is S into L into tau upon √2, and you'll get the answer. So the correct answer is C. Now, since in this topic we have covered both design of riveted joints earlier and then welded joint, so let us see the example on riveted joints also. A horizontal plate has been joined to a vertical post using 4 rivets. This has been asked in the examination, gate examination. So we will solve this. This type of problem is nothing but the riveted joints subjected to load, eccentric loading in the plane of bolt. So this is in the plane of bolt type. Now wherein we can see this, that the load applied P is 400 Newton, and the eccentricity of the total riveted structure is 500 mm, the distance from the edge, and the distances between the rivets are nothing but the 40 mm. So here the direct shear load, I have solved this problem. Say direct shear load P dash is equals to P upon N. So P dash is 100 Newton. Then for secondary shear load, we can directly use P2 dash, the formula itself. But how to calculate L1, L2, L3 and L4? So to calculate L1, L2, L3, L4, I have drawn this simple arrangement of rivet, simple geometry of the rivet, where this point shows the center of gravity wherein we have located, because this is a square setup. So every distance is 40-40. So divide by 2. So 20-20. I have calculated this length L1. Similarly, L2, L3 and L4 may be calculated in the same fashion. So we have calculated L1 under root 20 square plus 20 square. And there we go. L1 is equals to 28.28. Now this L1 is equals to L2 is equals to L3 is equals to L4, since all the four rivets are equidistant. So we have calculated this and found the answer. I hope you are understanding this numerical. Again, the same thing, but a single riveted lap joint. Lap joint is there. So in the lap joint, we can say that in the lap joint. So the lap joint, again, the very basic entity is to be there. Yes, sir. So the lap joint, I think this is quite visible now. Okay, so a single riveted lap joint of two similar plates. Now, in this case, width of the plate is given, thickness of the plate is given. This is width, this is thickness. 5 mm. Number of rivets, there are 3 rivets. Diameter of rivets, diameter of rivet is a dr, but diameter of rivet hole, obviously, it has to be actual. A slight larger hole should be there. Stress of the rivet, allowable tensile strength of the plate, because we are much concerned with the plate itself. What is our demand? The demand is very simple. If the plates are to be designed to avoid tearing failure, this is very important aspect. Then maximum permissible load P in kilonewton is, so these are the 4 options: 83, 125, 167, and a simple formula is used. The tensile or the tearing failure of the plate along the rivet, along the line of rivet, is stress into area. Now, how much area will be covered, since there are 3 rivets? So the total width minus 3 into diameter of hole, because it may tear off from the hole, not from the rivet. Rivet will tear off in shear, simple shear, but this is for the plate itself. So into the thickness of the plate will come into picture. So this is the solution and just the hint, and this is the answer, 167. So I hope we have understood these 2 problems for 2 marks as far as riveted joints are concerned, and this is the basic explanation for in the plane of board. Thank you so much for attending this lecture on design of riveted and welded joint. Now we will shift to lecture number 4, that is very important and the last lecture in the series as far as design of elements are concerned. So we'll be sharing now the next element, that is and I hope everything is fine now. can make this a bit larger so that things can be covered up. So today's lecture, as far as today's lecture is concerned, we are inclined to go for a large number of mechanical components, wherein shaft, gears, bearings, springs, brakes, and clutch. Now, all these are the most important part of any mechanical design system. Up till now, what we have seen were the joints, wherein fatigue design, static loading, fatigue loading, and now the joints which we have discussed right now. And the last element is shaft. So we'll start with the shaft. Shafts are nothing but the circular rotating mechanical elements. When we say shaft is basically the spine of any transmission. The most important aspect is the shaft. Now, as far as transmission of power, mechanical power is concerned, the shaft is the generally circular rotating mechanical element which transmits power from the source generating it to the machine consuming it. So in my view, it is basically working as a postman. But in the process of power transmission from the source, how many sources are there which generate power as far as mechanical powers are concerned? The basically identified sources of power were IC engine, electrical motor, and turbines. These were the basic identified sources of power. Now, shaft does not produce power of its own. Basically, it only transmits. So these are the sources. Now, from these sources, this shaft tries to transmit power from source to some sink. Now, that sink may be machineries, assemblies, any good thing, automobiles. So it transmits power. In automobile, just take the example of automobile. In that case, our internal combustion engine is forming the power, mechanical power, and now Mr. Propeller shaft through gearbox and clutch assembly is transmitting power to the rear wheel if it is a rear wheel drive, differential assembly, and then the automobile moves. So this is shaft, very important. Now the shafts may be solid or hollow depending upon the application. The strength of shaft for hollow as well as solid will be calculated, and depending upon the application we can use. In marine application we generally go for hollow shafts. Yes, in marine application we generally go for hollow shafts. So this is the basic definition and the application. As far as types of shafts are concerned, there are basically three types of shafts. Transmission shaft, just now I have told you. Propeller shaft, it transmits power from one, that is the input shaft, to some input to some output with the help of this transmission element. The next is machine shaft. This is basically the integrated part. The best example is machine spindle. Now you take the example of lathe machine, wherein we can say that the chuck is mounted on the spindle. So spindle is the machine shaft. Crankshaft is the machine shaft. Yes, it is a machine shaft. It is the integral part of that particular system. If you try to remove that integral part, the entire system will not work properly. And the third one is axle. For axle, I must emphasize on this fact, although it comes under the category of shaft, but it is a non-rotating member and generally used to support the rotating members, that is wheels, in automobiles. Just so you might have heard this name, dead axle and live axle. So dead axles are nothing but it does not rotate itself, but it helps in rotation. It provides rotation to the wheels. Whereas live axle means the differential assembly. The next element, generally the materials used, ferrous, non-ferrous, both the materials are being used. Specifically, ferrous materials are used for Industrial application, hot rolled plain carbon steel, cold drawn plain carbon, alloy composition, alloy steel. Not many are there. Now we'll come on to the design consideration. Now when we say we want to design the shaft, the basic question which arises, how many different types of load will act on the shaft? Now, this is very important aspect. How many different types of load will act on the shaft? So the shafts are generally subjected to only torque, may be subjected to only bending. There are a number of examples wherein only torque will be acting. Now you take the example of railway axles where only bending will be acting because friction is say very minimum friction is there, so we can directly take that it may bend. Combined twisting and bending, you take the cranks of our bicycles. Maybe there are maybe chances are there that a shaft assembly of the shaft may be subjected to all the torque, bending moment, axial thrust. Now you may take the example of your propeller shaft of your marine or the large ship. So hence we have classified the design consideration based on strength and stiffness. Rather, to be more precise, and generally used term is rigidity. So again, we'll come on the rigidity part. So design of shaft based on strength. So just now I have told you about all these four things. This is the basic equation, T by J, where T is the twisting moment of the torque, J polar moment of inertia, G modulus of rigidity, theta angle turned by the shaft when some torque is applied over it, over its length L. So now when we say the shafts are subjected to torque, it means T by J is equals to tau by R will come into picture. So tau T by J is equals to tau by R. But this induced torque should always be less than permissible torque. So here are the polar moment of inertia of shaft about axis of rotation. For solid shaft, pi by 32 d to the power 4, and for hollow shaft, it is do raised to 4 minus di raised to 4, where do and di and do are the internal and external diameters of a hollow circular shaft. The next is, if the shaft is subjected to bending moment, in that case, the basic equation of bending or the flexural formula M by I is equals to sigma B by Y is equals to E by R. Now E by R will not come into picture. So here we will directly write it as sigma B is equals to M by I into Y. Where what is bend, sigma B? Sigma B is the induced bending stress, which should be less than permissible stress sigma T. Now as far as I, moment of inertia is concerned, because y is the distance of the outermost fiber from the neutral axis. So this is y. So I is pi by 64 d raised to 4, and again for hollow circular shaft it is do raised to 4 minus di raised to 4. Shaft subjected to combined twisting and bending moment. In this case we'll have to go for the equivalent bending moment and equivalent twisting moment. So again the tau and sigma B we'll have to add using basic principal stresses theory, that is maximum stress theory and maximum shear stress theory. So we'll use these two theories to calculate the diameter of shaft. See, these are the theory, maximum shear stress theory. So this is how we'll calculate or we'll substitute the value of sigma B and tau in this equation, and we'll get this equation. So under root m square plus t square is called as equivalent torque. The same thing, maximum principal stress theory, again the same thing is there. Now m plus under root of m square plus t square is known as equivalent bending moment. Now shafts subjected to axial load. As I have told you, in marine application, in ships, the propeller shaft on which at the forefront there is a fan of that propeller. So that fan which is rotating, will have to overcome the resistance by the flowing ocean. Yes, and that flowing water or the ocean will apply an axial thrust on this shaft, and due to this axial thrust, the shaft may get displaced from its bearings. That's why we have to apply thrust bearing there. Now, another approach to solve the problem of on the design of shaft, when we are considering all the three parameters: twisting, bending, and axial thrust. Please mind well, twisting, bending, and axial thrust. In that case, ASME code will come into play. Now, why does we use ASME code for the shaft design? Because it is considering both the aspect, that is shock and fatigue. Shock and fatigue, because shock will be there and fatigue will be there, because it is a continuous process, a repeated process wherein cyclic load will act on the shaft. So that's why KB and KT are the two important conditions or two important parameters that are to be used in solving the numericals, because it yields a satisfactory result, a safe design. The next, these are the some values for gradually up if the load applied is gradual, because this type, that is the classification, depends on the nature of application where we are applying these shafts. So gradually applied, suddenly applied with minor shock, and suddenly applied with heavy shock. In that case, the value of KB and KT may be directly considered from the table, data book table. The next aspect is design of shaft based on rigidity or stiffness. Up till now, we have discussed about the design of shaft based on strength, torsional strength, both solid and hollow. Now we will look into the basis of rigidity. Now, when we say stiffness, it is resistance to deformation. So, there are two types of rigidity. Number one is a torsional rigidity, wherein we say that the shaft will fail in twisting moment or due to twisting moment. So these are the basic parameters wherein torque is applied over the length L with polar moment of inertia of the section as J, and G is the modulus of rigidity, that is the material property. So this is the basic element wherein we can say that torsional rigidity, G into J upon L, that is T by theta. T by theta is also known as torsional stiffness, T by theta. The next is lateral rigidity. Now, when we say lateral rigidity, it means that the shaft, obviously the shaft will be supported on the bearings. The shaft will be supported on the bearings. And if some load is applied over this, not always some load, because always there will be mountings. There will be flywheel, there can be clutches, there can be pulleys, belt drives, there can be, so any good mounting can be there on the shaft, which may try to deflect the shaft, which may try, say this is the shaft, so it may try to deflect the shaft, so the shaft may bend, and we don't want it to bend. So we have to design it based on deflection formula. That's why M by EI is equals to d2y by dx square. This is the basic deflection formula for beam, because we are considering for the lateral rigidity, we are considering shaft to be as a simply supported beam. Now here are some 1 mark questions, because again it is very important as far as exam point of view. According to ASME code, maximum allowable shear stress is taken as percentage of yield strength or percentage of ultimate strength. Now, I must say, before giving answer to this issue, ACV code considers yield strength as well as ultimate strength, but the design stress, the maximum allowable stress, shear stress, obviously shear stress is taken from this particular formula or the condition, and the condition is 0.30 times of SYT and 0.818 times of SUT. So the correct answer is 30 and 80, 30 and 18% basically, because when we use it, we'll have to use it as the tau allowable or tau max is equals to 0.30 SYT or 0.18 SUT. So the correct answer is 30, that is A, x is equals to 30 and y is equals to 18. The next, again the very important aspect, the next is, if allowable shear stress in the shaft is 70 Newton per mm square and torsional and bending moments are this, find the diameter of shaft. I don't think this is a very difficult task. You just scroll the PPT, then you'll get the answer, wherein we can directly say M is there, M is there, T is there. Okay, this is T, capital T is there. So this is torsion and bending moment. Either way you can go for this. So the answer is C. So please solve. You may take this as M, because since it is showing an hierarchy, and this as T. So this you can show this. So this is question number 2. This is question number 2. Next, question number 3. If yielding strength is 400 megapascal, then find the permissible shear stress according to ASME standards. Again, a very simple element, since you have got yield strength. Just now in the first question I have explained you, if yield strength is there, then what we'll have to take? Say the answer. So next is flexible shafts have. So the answer is obviously flexible shafts have high rigidity. So I think we must finish up with shaft. Again, I must not mention this, but due to paucity of time, we must go through a bit faster, but the explanation will be there all the way, so you can see the slide or the videos later on also. Design of gears. Gears are nothing but the toothed mechanical elements. These elements meshes with each other and transmits power from one shaft to another, or the input shaft from input shaft to another. Gears are nothing but the mountings over the surface of shaft with the help of some key. Now these gears are used where the center distance between the shaft is less as compared to belt drives and chain drives. Yes sir, please mind this well. Where the center distance between the two transmitting shafts are less, then we use gears as the transmitting element. Now as far as types of gears are concerned, spur, helical, these are the most widely used and designed element, whereas there are a number of different gears, including worm and worm. Including worm and worm. So this is how the gears will work. Next, you can see the diagram itself. Now the nomenclature. When I say nomenclature, it means how the gears will be represented. And how the design will be included. So this is the basic diagram of gear teeth, wherein there's a face width, This is the addendum and dedendum. You can all very well know this, but the most important part is flank size, face, because we calculate face width also. Yes, it is one of the parameter. Since it was very difficult to describe the entire design procedure, but I'll try to brief it up. So this is the minimum number of teeth on pinion to avoid interference. Now, how does interference occur? Because when we go for the profile cutting of that gear tooth, in that case, either cycloidal, please listen to this carefully, either cycloidal or involute profile can be cut. Now, these profiles, when cut on the circular, say, gear blank, in that case, the phi, the value of phi, pressure angle is plays a vital role. Now, these pressure angle may be 14.5 degree, 20 degree, either full depth or stub. Stubbing is also there. So, in this case, these are the recommended values of minimum number of teeth on the pinion to pinion. On the pinion, obviously, pinion will be the smaller gear and gear will be the larger gear. So, generally, all the gears we used to call pinion as a smaller gear. We know by the terminology, pinion means smaller gear and the gear means larger gear, size, based on size. Now, this gear tooth, rather to be more precise, gear tooth is analyzed by considering, because we have to calculate the strength of gear tooth. When I say strength of gear tooth, it means that the gear tooth, this gear tooth should withstand, please listen to me carefully, it should withstand two basic type of loading. Two basic type of loading. When I say two basic type of loading, it means that both static as well as fatigue loading will be there. Both static as well as fatigue loading will be there. Now, when we want to design based on static loading, we have to consider the tangential tooth load on the gear tooth. The tangential tooth load on the gear tooth. And due to, and say, in any case, if this is the driven part, if this is the driving part, if this driving part is trying to rotate this driven part, then obviously it will apply some force, and that force is nothing but tangential force. Now, due to this tangential force which is being applied on the gear tooth, this gear tooth may be subjected to bending if the sufficient strength is not given to the gear tooth. So this is called the design of gear based on static criteria. And the equation is Ft should always be either less than or equal to bending strength Fb. Now, based on this, we can design the gear, any gear, let it be spur, helical, bevel, O-worm gear. The basic criteria is static condition. Now, the dynamic condition, that is when it is in rotating. In that case, in the dynamic condition, we have to calculate the dynamic load on the gear tooth as well as the wear strength load or the wear strength of the gear. That's why we compare these two parameters Fd and Fen. We compare these two parameters Fd and Fen so that the dynamic strength of the gear can be well calculated and made safe. That's why when we calculate based on static condition or calculation, we calculate the module, the face width, n number of parameters. From there, we calculate CV, we calculate VP, we calculate Levy's factor, modified Levy's factor. I'm coming over to this and that issue. And in that case, we have to have the safe design. First based on wear and second based on endurance. So Mr. Wilford Levis has considered this gear tooth as a cantilever beam. a simple cantilever beam, a simple cantilever beam. He has considered it as a simple cantilever beam. Now, based on this, because from this aspect, from this point, Ft will be applied, tangential thrust will be applied. And due to this tangential load, this particular gear tooth, which is assumed to be a cantilever beam may get bent, And he has given the simplest formulae for this particular aspect, so that the gear tooth may be safe in bending also. Now, as far as modes of gear failure are concerned, because see, the design aspect which I have explained to you is based on both static and dynamic condition. Now, this is the very common say gear failure. These are the common gear failures when scoring, wear, pitting, plastic flow, and tooth fracture. Out of this, we are very much concerned about scoring, pitting, wear. Very much concerned. That's why we use different types of heat treatment processes to improve the surface hardness. We improve the surface strength of the gear so that wear can be avoided. For pitting to be avoided, we have to design with minimum error, because we have to consider error also. There are some permissible error, there are some probable errors, which is by virtue of which type of class we are using. That is class 1, class 2, and class 3 types of gears. So these are the different types of gear failures. Now, some basic questions. You can very well see which of the following can be used for power transmission in intersecting shaft. And I think the answer is very simple: bevel gear. Which of the following are true for worm gears? So worm gears are, I'll come over this issue. Worm gears are basically low speed reduction ratio, that is D. So before finishing up, I know because the design is to be discussed in detail, but since again I'm repeating the same reason, so now again look at this particular. Now here, spur gear and helical gears are used or will be used when, please mind well, when two parallel shafts, when the power is to be transmitted between two parallel shafts. Now, if I want to transmit power between two parallel shafts, then I may go for spur or helical, depends. Double and single, you don't worry. If the power is to be transmitted, please listen to me carefully. If the power is to be transmitted between two perpendicular shafts having intersecting axis, this is very important. Between two perpendicular shafts having intersecting axis, the axis of the driver and driven shaft will or should intersect at a point. Then in that case, I'll be using bevel gearing. Let it be spiral, let it be hypoid, let it be straight, that depends on tooth profile. But the basic condition is it should intersect. Now, it is not a necessary condition that our gear, that is the shaft which are intersecting, should be at right angle only. It may be acute, less than 90, it may be obtuse, greater than 90, or generally 90 for bevel gear. Now the fourth criteria is worm and worm gear, wherein this type of gear, the axis of the driver and the driven shaft will be perpendicular but should not be intersecting at all. And that's why the worm gear comes into picture. Worm and worm, wherein that worm gear is a simple arrangement of a worm rod and the circular gear. So this is the simplest arrangement. On this worm rod, there are number of teeth. Basically, for rod, we used to call it as a threads. So one or two or three number of threads are there. It will mesh with the gear tooth profile and transmits power. The velocity ratio of worm and worm gear is very high because only one or two tooth gets meshed with the gear to number of gear tooths, so the velocity ratio is very high. Whereas as compared to spur and helical, it is low, 4, 6, 8 times we can transmit the power. But as far as worm and worm gear is concerned, so these gears are tremendously reduces the velocity ratio or increases the velocity ratio. Generally reduces the velocity ratio. So this is the basic terminology of design of gear. I'm again repeating, the strength of gear depends on these two criterias. Number one, static condition, and number two, dynamic condition. In static condition, the tangential tooth load and the bending of the tooth plays a vital role in calculating the parameters of the gear tooth or the parameters of that particular design. And number two is dynamic condition, wherein we have to calculate the dynamic load, wherein we calculate endurance as well as wear loading. So I think we should stop here for gear or design of gear, because it's a very vast topic. The next is design of rolling and sliding contact bearings. Now, how to define bearing? Now, please mind well, the word bearing means to take up. But here the bearings are the machine or mechanical element. We primarily see bearings as a supporting elements. No, bearings are intended for guiding the motion of the shaft. Because if there are no bearing surfaces, say the contoured surfaces, now you may see, if it is visible easily, say this is the shaft. If this shaft is rotated by some belt drive or gear drive, now if this shaft is not holded, or if this shaft is not rested on the bearing, then it may travel in this fashion. So the guidance of the motion by the bearing is an important factor in the design of bearing. Number one, it guides the motion. Number two, it takes up the load. Yes, it takes up the load. And number three, it offers minimum friction between the shaft and the bearing surface. Now, as far as classification of the bearing is concerned, prior to the classification, we must say that how many different types of motions will be involved. So there are two types of motion that will be involved. Number one is a rolling motion, wherein the shaft is rolling over another surfaces. And the next one is sliding. So sliding means it will have some surface area. Yes, either line contact or surface contact. Wherein in rolling, either line or point contact. So line contact is being reduced or tried to minimized from line contact to point contact. And that's why we are using generally ball bearings. Roller bearings are also there. In automobiles, maximum of the time thrust or roller bearings are being used. So the classification of bearing, depending upon the direction of load, radial bearings, that is obviously direction of load. So the diagrams are self-explanatory. Thrust bearings to support the load and acts parallel to the axis of the shaft. So these are the two types based on direction of loading. Now, depending upon nature of contact, just now I have discussed sliding contact bearing, engine crankshaft, these are the applications. You can see it. And rolling contact bearing. These are the very much, say, familiar part as far as mechanical engineers are concerned or the general public is concerned. These bearings are nothing but the ball bearings used in bicycles, in automobiles, in machineries, in fan. So this is much talked bearing. Now, design of sliding contact bearing. This design of sliding contact bearing largely depends upon the type of lubrication. Yes, sir. The type of lubrication. The different types of lubrication which we generally use is hydrostatic lubrication, wherein a lubricant, either oil or gas or air, is pumped from external source between the shaft and the bearing pad surface, so that the shaft surface can be slightly separated from the bearing surface, so that minimum friction should be there, and this type of arrangement is known as a hydrostatic type of lubrication. The second type is hydrodynamic, which is most widely used, as the hydrostatic type of lubrication is a costly affair as compared to hydrodynamic. Now, what does this hydrodynamic does? This hydrodynamic action begins within the assembly itself, whereas at the start of the motion, the shaft, due to its weight and the loading due to its mounting, touches the, now please concentrate on this diagram, touches the surface. So this shaft or the journal is touching the bearing surface. The moment it starts rolling, now this shaft at low speed will try to climb on the surface of bearing. Will try to climb on the surface of bearing, and due to this, the entire assembly is filled with the fluid. Yes, SAE20, SAE10, SAE30 type of lubricating oil, having a very good viscosity. So it gradually occupies the space at low speed and try to separate the surface of shaft from the surface of the bearing itself. So there comes a thin or a thick film of lubrication, as if we can say, that it is trying to separate the entire shaft or the entire assembly from the bearing surface, and will offer minimum or no friction at all. But in this case, the starting and the at the starting of the motion, at the end of the motion, the friction will be high. Otherwise, the rolling friction is very low. Again, the second aspect, Sommerfeld number. In the design of journal bearing, we have to consider various parameters, of which without Sommerfeld number, you cannot design a sliding contact bearing or the journal bearing. It is so important. It is so important that it includes all the maximum design parameters. The radius of the shaft, that is again very, very important. The coefficient of friction, the rotation RPM, the pressure or the bearing pressure, that is again very important. So radial clearance is also there. Radial clearance, C is there. So radial clearance between the journal, that is the shaft, and the bearing center, that's again a very important aspect. So this Sommerfeld number, if we know this Sommerfeld number, we can very well design the journal bearing, because a large data is available in data books. Now, based on that data, we can very well calculate, we can very well select the parameters from the data book itself. So I am not discussing in detail regarding the design steps. The next one is rolling contact bearing. Now, as far as rolling contact bearing is concerned, this is the much familiar diagram wherein balls are inserted between outer race and inner race, and it is generally used in the most application generally. Now, here I am giving a brief account of how to select a bearing from manufacturer's catalog, because you have to select the bearing from manufacturer's catalog based on different aspects. We have to calculate a radial and axial load, because when we say this is the bearing, we have to calculate the radial as well as axial load acting on the bearing. Then diameter of shaft. Then we have to select the race rotation factor V, and again we have to calculate both radial as well as axial thrust, and then we have to calculate the dynamic load acting on the bearing. So these are the equations wherein the life of the bearing plays a vital role in the selection of the bearing. So this is the dynamic load carrying capacity. See, yeah, dynamic load carrying capacity, and then you have to choose the higher side, higher value. Now these are some of the important terms in the design of that rolling or the ball bearing, rolling contact or ball bearing. That is the rated life of bearing. Life of bearing is the number of revolutions or number of hours at constant speed that the bearing runs before the first evidence of fatigue crack in the balls or races. So life of bearing is expressed in terms of statistical average life of group of bearing. That's why the statistical life is given by rated life or life in million revolutions. You will come to see this also in the later part. That is 90% of the bearing will complete or exceed before the first evidence of fatigue crack. It is also known as minimum life and L10 life of bearing in million revolution we generally calculate. Now reliability is again the important issue, because a reliable design will ensure safe operation of the bearing. So these are the basic relation wherein L10 is a rated life and life of bearing corresponding to percentage reliability. Generally we assume 90% reliability. If not, then we'll have to use this formula to calculate the reliability ratio. Now load life relationship, again L10. Here C is dynamic load carrying capacity, P is equivalent dynamic load, which we have calculated in the previous this one. So this is the P, equivalent dynamic loading. You have to calculate it and then substitute the value. As far as K is concerned, load life exponent 3 for ball bearing. Generally 3 for ball bearing we use, and then based on this equation we can calculate or select the rated life, and then we can calculate the dynamic load carrying capacity. Based on dynamic load carrying capacity, we can directly select it from manufacturer's catalog. Directly select. So I hope that is brief insight is there to calculate how to correlate or calculate the load life relationship. Now coming to the next design, a very important factor which provides us cushioning comfort at home, at offices, on the roads, in aircrafts, everywhere, that is the spring. So it's an elastic member basically. It's an elastic mechanical element which gets distorted when some external load is applied and regains its original shape when it is removed. But in the process of distortion, it gives us comfort, cushioning, shock absorption. It doesn't only used for shock absorption, it is used to apply some force. As in toys, we can say that as in toys we can apply the load. So it can be again used to store the energy also. It can be used to measure the forces also in spring balance. So these are the various examples wherein we can say that the applications are wide for the springs itself. So these are some of the diagrams which we are all much aware of. Some of the terminologies of helical compression spring, I just wanted to brief this aspect because this issue is helpful in designing the helical spring. Now this is the largest or the nominal diameter or effective diameter we say. This is the pitch, this is the diameter of wire, this is free length. When some load is applied, this is called compressed length. So this is the deflection, but this is not the maximum deflection. Now the third diagram depicts the compressed or solid length. Now here, if we say one coil is touching the another coil, so that is not a good design. That is not considered to be a good design. Why? Because when one coil is touching the another coil, even though it is in the solid state or compressed state, then in that case it will try to impact, it will try to crush, so crushing stress will be developed. So that's why the factor is considered. Yes, stress factor 10% or 15% of the total compression length is given for that particular component. It should not touch the helix, of the wire. The coil is made in helical form. So that when the coil is compressed, it will absorb the load. It will absorb till, if the rod is removed, it will regain its original shape. So these are some of the terminologies in use. Now, as far as the design of helical springs are concerned, the stresses in helical spring, because helical springs are subjected to both number one, twisting, and number two, bending. It may be twisting, it may be bending, it may be both. So in that case, in both the cases, the most prominent part is a shear. So when it is subjected to twisting, it may be subjected to primary shear or the torsional shear, and it may be subjected to direct shear. Now this primary and direct shear together we have to combine, we have to add these effects, and we'll have to calculate the resultant shear stress. Now based on, you can see this is the simplest equation wherein we have torsional shear stress and direct shear stress. Direct shear stress means, suppose this is a spring. If some load is acting on this spring, and if this spring gets in, a slight deviation is there along the line, then it may fail. The wire, say this is coil, but the wire is made helical into a coil, so wire may fail in direct shear. That's why the formula or the area is considered as pi by 4 d square. The second one is a torsional shear. So here comes the torsion equation. T by J is equal to tau by R. Adding these two will give you this one. Now there is a factor known as a shear stress factor. Now this shear stress factor is nothing but the correction factor. Which is used to design the spring. But this correction factor, shear stress correction factor, we generally used to call it as Ks, only considers shear stress only. Whereas Mr. Wall has considered a Wall's correction factor taking into account, please mind well, taking into account the stress concentration due to curvature. So the curvature effect of the helical spring is to be accounted, and that has been done by Mr. Wall, and that's why he has given a factor 4c minus 1 upon 4c minus 4 plus 0.615 by c. So this is the stress concentration factor or the correction factor in helical springs. So generally Wall's factor, since it is considering both the aspect, is widely used. The another type, semi-elliptical laminated spring, it is very famous for your automobile, basically the commercial vehicles, even passenger vehicles also, and it is designed on the basis of bending. The entire design is based on the bending effect. So bending and deflection, this is the two basic equation of how we design based on bending stress and deflection. The very interesting aspect of this particular design is when we say to design this, say, spring, the entire load is supported by these two eyes. The first leaf is called as a master leaf, and there are 1, 2 or 3 supporting leaves known as extra full length leaves. Below this extra full length, we have got a number of graduated leaves fixed or held together by U-bolt or the central tensioning band. Now, when the load is applied over this particular spring, it deforms. It deforms. Now, when we say it deforms, the gradual leaves will come into force or will come into play when the load displaces or deforms the master leaf. So they will come for rescue, and thus the load is shifted from master to full length, and then full length to graduated, and thus to the axle, and thus to the tire. So semi-elliptical laminated springs are most widely used and most important part. Rather, to be more precise, it works as a structural member in your automobile, in our automobiles, in railway wagons itself, because the structure, it works as a structural members means what? It helps in taking up the load also, as well as the vibration absorption. So this is all about the design of spring. Coming over to the second last point, that is design of brakes. Now I must say that brakes and clutches are the important mechanical components in the controlling of speed, either in machine tool or in automobiles. Now when we say brakes, to decelerate, the brakes are the mechanical elements which are employed to regulate the speed. Now when we say regulate, the inclination is more on stopping the rotating mechanical element, that is shaft or a drum. Shaft or drum. So brakes are the devices that dissipate kinetic energy of the moving parts of a machine. In mechanical brakes, the dissipation is achieved through sliding, obviously the sliding friction. The sliding friction will be there. So depending upon the direction of application of braking force, the mechanical brakes are primarily of three types: shoes or block brakes. So this is the shoe brake. Number two, band brake. So these are the bands. And third is disc brake, which are now most commonly used in our two-wheelers. Generally disc brakes are there because the braking action is very fast and very convenient also, but along with this, it is very dangerous. So you must be very careful. We all must be very careful as to, while applying the brakes, you have to be very careful, because the sudden stoppage may cause inertial effect, and the consequences we all know. So these are the brakes. These are the two types of brakes, wherein the action will explain the parameters. Now please consider this diagram again. So I'm talking about the shoe or block brake. A simple lever is pivoted at one end, while some force with the hand or the foot or the spring arrangement may be applied at the free end. Here this is a shoe or a metal block whose contour, whose surface, outside surface, is in conformance with the drum, surface of the drum. So the surface conformance will be there between the two shoes and the drum. Now, since it may rotate in clockwise or anti-clockwise, depending upon this, we will calculate the effort applied. Because the load arm will be there, effort arm will be there, we'll have to apply this. Friction will play a vital role in both the design of brakes as well as in clutches also. That's why we must take care of the friction involved in the design. Now let us consider the mechanics behind this single shoe brake, wherein if you apply this load P in downward direction, then on this shoe a resistive force will be applied by the drum on the shoe. The next, the fulcrum point will be subjected to two reactions. That's why, please mind well, the rotation of the drum, that is clockwise or anti-clockwise, is an important aspect in deciding whether it is, if it is rotating clockwise, then the forces will be calculated with reference to taking moment about some point. So generally that point is pivot point O, or the reference point O. Then in that case, this is the equation wherein for clockwise rotation and for anti-clockwise rotation. Now, using Coulomb's law of friction, the following results may be obtained. For clockwise rotation, how much F or P will be required? F or P, both can be calculated from these two equations for clockwise and anti-clockwise rotation. Now, you may please consider the band break. So, in simple band break, one end of the band is attached to the fulcrum. So, this is again you may see that this is the free end and this is the fulcrum point. Now, simple band break is also there, differential band break is also there. In differential band break, the differential point occurs between this T1 and T2, somewhere here, not at the center always, but it will have some inclination in this fashion, and the lever is known as a differential. So again, this is the basic design criteria wherein the torque which is to be supplied by or which is to be stopped by this band will be calculated with respect to the friction at the bend. The design involves again effort applied by the operator. So this is the band break, and previously it was the, you may please see, this is shoe or block break. So this is how the design will include all these parameters. Now the last one, clutch. Again the friction drive. The clutch is an important element in the power transmission system. You just take the example of our commercial vehicles or passenger vehicles. Now, what is the basic outline of your transmission? Engine developing some power is to be transmitted from engine to the rear wheel, if it is rear wheel or front wheel drive or four wheel drive, doesn't matter at all. So after engine, the engine will transmit, or the engine will produce a fixed amount of RPM, a fixed amount of torque. After the engine, we will be having a clutch assembly. After the clutch, we'll be having a gear assembly. After gear, we'll be having some shaft assembly or transmission elements. Now, why do we require a clutch assembly between the engine and the gear assembly? Because we want to shift the gears. Without stopping the prime moving element. That's why clutch is installed there, so that continuous power can be supplied at a variable speed without stopping the engine. So what does this clutch do? This clutch gets engaged by default, but it may disengage, so that due to the inertia of the gear pair which is there in the gearbox and the resistance from road to this gear, will try to minimize the speed of the transmitting gears, and thus gear changing or gear shifting becomes easy, so that shock may not be involved in gear changing. That's why we use clutch. Now, as far as definition is concerned, the clutch is a machine member used to connect a driving shaft to a driven shaft, so that driven shaft may be started or stopped at will without stopping the driving shaft. The use of clutch is mostly found in automobiles. So friends, these are the types of clutches wherein we say positive contact, friction, electromagnetic, and fluid clutches. Nowadays, fluid clutches are more in use. As far as positive clutches are concerned, square jaw and spiral jaw. Square jaw clutches and spiral jaw clutches are mostly used in on-load mechanical systems, wherein you have to engage the clutch by your own, so that if load is increasing or if load is decreasing. Friction clutches most widely used. Single plate clutch, as in our cars, multi plate clutch, as in our bikes, cone clutch in our bikes. You take the example of your automatic bikes, centrifugal clutch, your Activa, and the other mopeds, wherein we don't have sir gears. Arey na, that gears are there, but the criteria is something different. So centrifugal clutches are again very important. Then electromagnetic, electromagnetic. So electromagnetic is also there, and then fluid clutches. So this is the basic diagram of friction clutch. Single plate, rather to be more precise, single plate friction clutch. Because when we say single plate clutch, so these are the basic entities, the driving shaft and the driven shaft, and having some friction linings in between. These are the basic parameters of a design wherein we use uniform pressure theory and uniform wear theory. These two theories are used in the design of brakes also and in the design of clutches also. This theory is based on the concept that when the friction surfaces are new, please mind well, the pressure applied by the driving side will be uniform on the driven side. The pressure applied by the driving disc on the driven disc will be uniform throughout, because the surfaces will get equal distribution of pressure, because since the surfaces are new. So in that case, the mean diameter may be calculated by using this new theory, that is uniform pressure theory. But generally these surfaces gets torn off, these surfaces gets worn off, wear off. So the next theory comes into picture is uniform wear theory. Now due to heat, due to friction, due to heat, the surfaces may get torn off from different parts of that particular surface. But we have to consider that the pressure applied by a driver plate on the driven plate, is uniform. The wear will be uniform. That's why it is uniform wear theory. And this is the most widely used theory in the design of clutches. Now, this is the basic comparison between uniform pressure and uniform wear theory, wherein the diameters and some statistical data is given to compare, just to compare how much a difference would be there. This is multi-disc clutch in your bikes, as you might have seen this, having steel and bronze discs in between. This is the governing equation, wherein we say that this governing part is again holding the mean diameter concept. So thank you so much. As far as the design of machine elements is concerned, we have covered the basic components of mechanical system. See again, the design part, mostly I have tried to cover it up, because the basic design elements are there in our slide. So best of luck, and I hope you have got the things. Thank you so much. Thank you very much. Madam.